Good morning, students. Today I will discuss an AC circuit containing only inductor. We will discuss that what is the phase relation between EMF and current in this video. Suppose an ideal inductor of inductance L is connected to a source of alternating EMF E is equals to E naught sin omega t. As the alternating current I flows through the inductor, then an EMF is induced across the inductor and its value is given by minus L di upon dt, and it opposes the growth of current in the circuit. So the net EMF across the circuit, net EMF across the circuit, it will be equal to this E plus the EMF induced across the inductor. So it is E minus L di upon dt. As we know, there is no potential drop across the circuit, so the value of E minus L di upon dt will be 0, or from here di upon dt is equals to E upon L, or E is equals to E naught sin omega t upon L. From here we can write di as E naught upon L sin omega t and dt. Now integrating this equation on both sides, we will get integration di is equals to integration E naught upon L sin omega t dt. On integrating di we will get I, so this I is equals to E naught upon L as constant. Sin omega t can be integrated and it will give minus cos omega t upon omega. So from here we are getting I is equals to E naught upon omega L cos omega t with a minus sign. Or we can write I as minus I naught cos omega t, or it is I naught cos minus cos omega t, I naught into minus cos omega t, or it can be written as I naught sin omega t minus pi by 2. So I is equals to I naught sin omega t minus pi by 2. This is the equation for instantaneous current across the circuit. Here this I0 is the peak value of current, which is given by E naught upon omega L. It is peak value of AC. Now we can see that current lags behind the EMF by an angle pi by 2. So this can be represented as it is E naught and this is I naught, having a phase difference of pi by 2. So it is omega t, and this is pi by 2. So this is the phasor diagram for current and EMF. Now this I naught, which is E naught upon omega L, can be written as E naught upon XL. On comparing this equation with Ohm's law, it is clear that XL plays the same role in the inductive circuit as R plays in the resistive circuit. So this quantity XL is known as inductive reactance. Inductive reactance. Or it is the effective resistance offered by the inductor to flow the AC through it. Now the value of AC can be calculated. Value of this inductive reactance can be calculated using the formula XL is equals to omega L, which is equal to 2 pi FL. For AC, the value of frequency is finite, F is finite. So the value of XL is also finite. XL is finite. It means that the inductor offers finite opposition to the flow of AC. This means AC cannot flow easily through the inductor. Now in second case, when a DC is passed through an inductor, for a DC, the value of F is 0. So XL is equals to omega L, or 2 pi FL will also be 0. It means that the inductor offers no opposition to flow of DC, or DC can flow easily through a inductor.